Continuing on the concept of RTL sequential components, we have done counters, registers, very long description for them. And now we are doing something called a shift register, another shifter. Shifter, remember when in combinational circuits, we said that we have 5 lines. We want to shift them. All you have to do is to put the line number 4 on line number 3, line number 3 on line number 2, so the wires cross. That's all there is to it. But then here, it's a register that has the shifting capability. So I'm going to do that, and shifters are useful for waveform generation, for dividing by 2, multiplying by 2, and or multiplying by 4. So there are a lot of uses for shift register, for serial data coming in and make turning serial data into parallel data, for making parallel data into serial data. So you clock in the whole data into the shift register, and then one clock at a time you start shifting the data out, or the other way around. So let's do shift registers, and it is simply built by this structure. Okay, take a flip-flop, and take a flip-flop. The output of it connects to the input of the next, and on and on. Okay. When clock arrives, now remember that these are either edge trigger or master slave. No transparency. If these components were transparent components, what would happen would be, as soon as clock becomes 1, the serial input would go from here to here, transparent to this, to this, to this, and then everything would be wiped out, and the serial input, whether it's 0 or 1, could go through the whole thing. Unless your clock is so narrow that you stop it somewhere in the middle. But transparency does that. Since you don't have transparency, what happens is this. On the edge of the clock, let's say this is 0, this is 1, this is 0, this is 1, and let's say this is 0. On the edge of the clock, let's say rising edge of the clock, each one takes its input, puts it halfway inside. Like, for example, I start from the left-hand side. It's easier, by the way, to start from the right-hand side, but just for the sake of illustration, I'm starting from the left-hand side. On the rising edge of the clock, this puts the 0 inside. On the first part of the rising edge of the clock, this puts this 1 inside, this 0 puts this 0, this one puts this 0 inside, this one puts this 1 inside. What happens to their outputs? Nothing. Nothing. On the second part of the edge of the clock, nothing happens to the input side, but then this one puts that 0 on the output. This one puts this 1 on the output. This 0 on the output. This 1 on the output. So look at what I had in red and what I have in blue. What I had in red was this on the output of the flip-flops. 0, 0, sorry, 1, 0, 1, 0, 1, 0. After the clock, what I have on the outputs is 0, which is the serial input, then 1, which is this one, 0, and 1. What it means is 1, 0, 1, 0 shifted one place to the right. You give it the next edge of the clock, shifts one more place to the right. That's why this is called the shift register. It's easier to analyze this from the right hand side. Okay, if you analyze it from the left hand side, make sure that you take the input, put it in the middle, and then later take the middle thing and put it on the output. If you do the left hand side, maybe there is a danger of you taking this 0 here, for example, and say, okay, this 0 replaces the 1 on the output, which it does, okay, but not immediately in 2 steps. And then you say, okay, this is 0 now. And then when you get to the one next to it, you say, okay, now the input of it is, by mistake, you get the blue value of the output, not the previous value, which was what you should have got. But then if you start from the right hand side, you don't have to worry about this, because you say, well, this one replaces this one. This 0 replaces this one. This one, the red one, replaces this. And then this 0 on the serial input replaces this, and therefore I have 0, 1, 0, 1. Okay? If you give it the next clock, it moves, the data moves one place more to the right. Okay? So I start with, let's say, 1 on the serial input, 0, 0, 1, 0. Shift it to the right, 1 goes here, 0 goes here, 0 goes here, the blue one goes there. So the contents of my register becomes 1, 0, 0, 1. Give it one more shift. This goes here, this goes here, this goes here. What happens to the right? Just appears as it has been kicked out. And then this one goes in there. And therefore you have now, after 2 clocks, 0, 1, 0, 0. Shifting. Give it one more clock. This 0 goes here. And then what you have on the output is 0, 0, 1, 0. Okay? So the key thing is that these are non-transparent. Okay, do I always want to shift right? Maybe not. Maybe I want to shift right today. Tomorrow I want to shift left. Or maybe I like the idea of parallel loading, so that if I don't want to use the shifting feature of it, at least I can use it as a register. What else I want it to do? Well, maybe I don't want it to do anything. Clock arrives and it does nothing. So this is a 4-mode shift register, often called a universal shift register. A universal shift register does 4 things. Shifts to the right, or let me start from 0. It has 2 mode lines, M1 and M0. Mode 0 means M1, M0 is 0, 0. It does nothing. It turns out does nothing is not really nothing. Okay? So let's do this with highlighter. Does nothing. This means that the output of each of the flip-flops goes back into itself. That is mode 0, or the input 0, 1, 2, 3, 0, 1, 2, 3. So if my mode inputs, which are these 2 down here, are 0, 0, I'm selecting the upper inputs of the multiplexers. The upper inputs of the multiplexers, notice how the output goes back to the input. Output of each flip-flop goes back to the input of the flip-flop, means that does nothing. Okay? The multiplexer, if Mode is 1. See what happens. What happens is exactly what happens here. The output of the left one goes into the input of this flip-flop. Okay? And therefore, see, this is going into this. This is going into this. This is going into this. And the leftmost serial in goes into this. And then where does the rightmost go? Well, the rightmost goes into serial out from the right, which is really nothing but that parallel output bit 0. That's mode 2. Mode 1, sorry. Mode 2 is this one here, left shift. Okay, so mode is 2. And what should happen, let's go back here. Right shifting means that this gets its input from the one to the left. Left shifting means that this should get its input from here. And therefore you are seeing here that left shifting, you have serial in from the right, which is this, goes into this, but then this output goes all the way to the input of the one to its left. This output, let me use somewhat of a different highlighter. This output, not through here, this output goes to number 2 of this. This output goes to number 2 of this, and this last output goes into serial out from the left. Okay, so I use 2 colors so that lines don't cross. And I guess they crossed anyway, right? Finally, I have the parallel loading, and that the path is so easy that I can use any highlighter color I want. Let's use orange, which I haven't used, and that's mode 3. Mode 3, if mode is 3. Okay, if mode is 3, each one of the flip-flops is getting its parallel input, and those are what goes on the output. It does 4 things: do nothing, right shift, left shift, and parallel loading. This is called the universal shift register. Let's do some Verilog, and then again remember that the register description that I showed you is this. Okay, there is the clocking and all that, and then the green area, which is the resetting and all that, and then you have this red area which says, okay, after the resetting and all that, this is the behavior of the construct that I'm describing. And therefore, now what you see here is that I still have positive edge of the clock and synchronous resetting. If reset is 1, then parallel output becomes 0. That's asynchronous resetting. So that's the green area I was showing there. So I'm going to do the same thing here. Okay. So this is if resetting is being done. If resetting is not being done, then you go into the else area. For the register, the else area was a simple thing. For the counter was a little bit more complex. For this one, you have 4 modes. M is the mode input. M is the mode input. That's a 2-bit mode. And then mode selects. If mode is 00, I'm using a case statement. A case statement is another statement that goes in the always statement. I've shown you so far signal assignments go in the always statement. If statements go in the always statement, conditional assignments do go in the always statement. Case statement also goes into the always statement. You can do this with if statement. Okay, if mode is equal to 00, do this. If it's equal to 0, else if it's 01, do this and all that. But then it's much easier to do a case statement. Let's do the case. Case M, that means if mode, then you have choices. These are my 4 choices. Choice 00, choice 01, choice 10, choice 11. Okay, these are my 4 choices. If choice is 00, do nothing. Do nothing means what? See, do nothing means the parallel output goes back into the input. And therefore, do nothing means parallel output goes into the input. Then I have the shifting right. Shifting right means what? Means the serial input from the left goes and sits in parallel output 3, and then everything else goes into the next bit. So what I do is, on the right hand side, I form serial in from the left, concatenated with PO3, PO2, PO1, that forms a 4-bit vector. I clock this 4-bit vector into the PO3, PO2, PO1, and PO0. Therefore, SIL goes into PO3, PO3 goes into PO2, PO2 goes into PO1, PO1 goes into PO0, PO0 is lost. Okay? And therefore, this is shift right. What does shift left do? Well, it does the same thing, except that the serial in from the right comes in, and then bit 0 goes into 1, bit 1 goes into 2, and then bit 3, the all 3 is lost. And therefore, what I have is here, serial in from the right comes in, okay? And then you concatenate here. You concatenate parallel output bit 2:0 with serial in from the right, and then that becomes parallel out that goes into the parallel out. And finally, the orange stuff. Okay. Mode 3, paralleling goes into the output with these multiplexers here. And that's the very long description of it. And what I want you to see here is that really doing these descriptions so far, that understanding of that flip-flop, that very first flip-flop was the key thing. And all you're really doing is adding more conditions, more constructs and all that, which is very software-like thing, which is not that difficult to do. All right, we are done with the shift register. We are done with the registers, up counters, 2 counters that were making the base of everything else that we said about counters. And also what we did was we did the very long description for a register, for a counter, for a shift register. Thank you.